Hi class, my name is Zach Whitaker and I'm going to be talking to you about the physics in the human mouth and the physics of chewing in the human mouth. The anatomy of the mouth is not as complicated as other parts of our body. Firstly, a fully developed adult mouth has 32 teeth, and that number includes the 4 wisdom teeth. 16 teeth live in our upper jaw, also known as the maxilla, and 16 teeth are in our lower jaw, also known as the mandible. There are 4 different types of teeth. These include the incisors, the canines, the premolars, and the molars. Humans have 8 total incisors. These are the front 4 teeth in our maxilla, and the front 4 teeth, the front 4 center teeth in the mandible. And you can see those represented by green here. So those are the incisors. The incisors are used to cut into your food. Next, there are 4 canine teeth. 2 in the top jaw and 2 in the bottom jaw. And these are represented by the red teeth here in the upper and in the lower. The canines, these are the 4 sharpest teeth in your mouth. The purpose of the canines is to tear up the incoming food, so to pierce and tear the incoming food. Next are the premolars or the bicuspids. Humans have 8 premolars, 4 on the top, 4 on the bottom. These are represented by the yellow teeth. So 4 premolars up top, 4 premolars up bottom for a total of 8. These are used for tearing and crushing food. And finally, we have the molars. These are the biggest teeth in the mouth. A fully developed human with all 32 teeth will have 12 total molars, 6 on the top and 6 on the bottom. The purpose of the molars is to crush and mash the food into tiny bits to make it easy to swallow and digest. And these are just some illustrations to kind of illustrate how the teeth operate. So this is how the incisors work. They cut and chop the food. The canines, they kind of stab and tear the food like Leonidas is doing here with his spear. And then the premolars and the molars, like I said, they smash the food and they kind of puree it so we can easily swallow and digest it. The teeth also have surfaces that are important to know when considering the mechanics of chewing. The dental term for chewing is mastication, so that's important to remember. So chewing is mastication. The distal surface of the tooth is the surface of the tooth that is located furthest from the center. So here you can see the distal of this tooth is over here and not here because this is further from the center, the midline of the mouth. So the distal is the surface of the tooth that is furthest from the midline. The mesial surface of the tooth is the surface that is closest to the midline. So mesial is the closest to the midline, distal is the furthest from the midline. The facial surface of the tooth is the surface of the tooth that faces the cheek or the face, so it faces out. The lingual surface is the surface of the tooth that faces inward, so it faces towards the tongue. And finally, we have the incisal edge and the occlusal surfaces. The incisal edge of a tooth references the sharp or pointed surfaces on your top and bottom 8 incisors and your top and bottom 4 canines. So those kind of come to a point, the incisal edge. The occlusal surface, on the other hand, references the chewing surfaces characteristic of the remaining teeth, so the premolars and the molars. These have, and you can feel it in your mouth, these have a larger surface area, so they don't come to a point and they aren't sharp, they're flatter. So that's the occlusal surface. When considering the physics of mastication, the surface area of your teeth the surface areas of your teeth are vitally important. The incisal edges of your canines and incisors have a much smaller surface area than the occlusal surface of your premolars and molars. Stress is defined as the force applied per unit area. As the surface area decreases, the stress applied to the object or our food becomes greater. As the stress becomes greater, the strain on the food also becomes greater. This is useful as we use our front teeth to deform and break our food into our mouth. So then we can use our molars, which can apply a greater force with a larger surface area to crush and puree our food. So we need our front teeth, the teeth that have a smaller surface area, to apply more stress so they can apply more strain on the food so we can break apart that food and get into our mouth like Guy is doing right here with the pizza. The stress applied by our teeth when biting into food must cause a strain within the food big enough to push it past its ultimate compressive strength. And its ultimate compressive strength is when that food starts to fracture. It's not when it totally fractures, but once it gets past, once the food is strained past its ultimate compressive strength, then it is starting to fracture. This can be well illustrated by a stress-strain curve. The first section of the graph is the food's elastic region, so right here. Any force applied within this range will not be sufficient to deform the food. The slope of the line in the elastic region is referred to as the elastic modulus, or Young's modulus. The next region of the graph is referred to as the plastic region. Any stress applied to food by the teeth within this region will leave the food permanently deformed, but it will not fracture the food. The point at which the food can no longer be plastically deformed and will fracture is called the breaking point, or the fracture point. Excuse me. It is also important to note that our teeth are not connected directly to our bone and gums in our mouth. Instead, a layer of elastic fibers made up of mostly collagen surround the tooth and hold it in place. This layer of fibers is called the periodontal ligament. This helps spread out and absorb the chewing load on our teeth. There's a few theories out there about how the periodontal ligament works, but the theory which I prescribe to regarding how the periodontal ligament operates is called the stretched fiber hypothesis. In this hypothesis, when a load, like food, is exerted upon the tooth, the periodontal ligament and the surrounding bone undergoes separate regions of high tensile stress and low stress. So you can see it right here. So if the food is coming in over here, the tooth is going to move slightly, and this side of the periodontal ligament, it's going to have a high stress and cause high strain over here, and then it's going to have low stress over here and low strain. One way to think about how the periodontal ligament works is with the following example. Consider a person jumping to the ground from a box, or from the ground to a box, a few feet in the air. Upon landing, as you can see that this girl is doing, the person will bend their knees. This extends the collision time, but lessens the impact force. The periodontal ligament works much the same way. Consider the work-energy principle. Here we can see work equals force times distance, and the force times the distance equals the change in kinetic energy that you can see represented here. That is the change in kinetic energy. This equation tells us that for a change in kinetic energy, the work required, or force times distance, will stay constant. So what this means is the periodontal ligament allows the tooth to move a greater distance upon impact. Thus, the force will decrease. So if the distance increases, as the periodontal ligament allows our tooth to do, then the force has to decrease because the change in kinetic energy will stay the same. So it allows, the periodontal ligament allows less force on the tooth because it increases the distance there. Another component of our mouth that plays a vital role in mastication of our food is our mandible. Of our two jaws, our maxilla on the upper and our mandible on the lower, the mandible is the only one that moves. So the maxilla is stationary, but the mandible moves. Our lower jaw can be thought of then as a lever. The fulcrum or pivot point of our lower jaw is the temporal mandible joint. It is located approximately right here, right where it's moving. The masseter muscle provides the force necessary to move our mandible. The masseter muscle is located approximately here, but I'll have another example shortly. To give a more detailed example about how the mandible works, consider that to chew a certain food, it requires a bite strength of 100 newtons. So to properly masticate it requires 100 newtons. According to Newton's third law of motion, if we are exerting 100 newtons of force on an article of food while chewing, the food then is exerting an equal and opposite force back on our teeth. But what is the force required by the masseter muscles to exert 100 newtons on the food by way of the mandible? So how much force does our masseter muscle need to exert to chew a food that requires 100 newtons of force? To solve this, let us assume a couple variables. The first being that the ramus of the mandible, which is at this part right here. So on either side, it's the angled part, the upward part. So the ramus is 4 centimeters long. Our second assumed variable is that the body of the mandible, so it's the rest of the mandible, the part that curves around and holds your teeth in place. We're assuming that is 8 centimeters long. Now that we have all our measurements, we can solve our problem. First, we know that the sum of the torques with respect to our fulcrum, or the TMJ, adds up to 0. So that's what this represents right here. The sum of the torque forces with respect to our TMJ equals 0. This force, next we know that the force the food is exerting, as stated before, the force the food is exerting down on our lower jaw is 100 newtons. It's because it requires 100 newtons to chew it, so it's going to exert an equal and opposite force, Newton's third law, down on our jaw. This force is moving in a counterclockwise direction because it's moving down, so that torque is going to be counterclockwise. This means that the torque produced by the food is positive. So we know that the torque is equal to the perpendicular force multiplied by the lever arm. Our next step is to multiply the force exerted by the food of 100 newtons by our lever arm distance, which equals a total of 12 centimeters. At this point in our equation of the summation of torque forces, we have 0 equals 100 newtons times the lever arm, which is 12 centimeters. Next, we consider the torque force applied by our masseter muscle. And here, as I stated before, is where approximately the masseter muscle is located in our jaw, in our two jaws. This is an upward force. It has to bring our mandible up to chew. So it's going to be an upward force. Because it is an upward force, it is going to be going in the clockwise direction. Thus, this will be a negative force, or a negative torque, excuse me. This is the force we're trying to solve for. So we must now multiply this unknown force, the masseter muscle force, by its lever arm, or the distance from the fulcrum. This distance, as stated above, is going to be the length of the ramus, and that is 4 centimeters. So our equation now reads 0 equals 100 newtons times that lever arm, which is 12 centimeters, minus, because it's a negative torque because it's going the clockwise direction, minus our unknown masseter muscle force times its lever arm, which is 4 centimeters. Now we can solve for our unknown force. So we move the masseter muscle times its lever arm over to the other side. We divide everything by 4 centimeters, and then we solve for our masseter muscle force, and that's going to be 300 newtons. This is the force required by the masseter muscle to exert a force of 100 newtons on an article of food. In pounds, 300 newtons equals approximately 67.45 pounds of force. The human jaw, on average, can produce a force of about 70 pounds per square inch. This comes to about 311 newtons. We have more chewing force in our molars. This is because the molars are located closer to the TMJ, or the fulcrum. When we chew with our molars, our jaw acts as a second-class lever. In a second-class lever, the load, or the food, is in between the force and the fulcrum. So you can see, here's our example of a second-class lever. If this is the TMJ, and this line is our mandible, the load is the food, we're going to exert our effort is going to go here, and the load's going to be in between that. So it's going to be a second-class lever. Because of this, it can exert more force on the food. A nutcracker, a classic nutcracker, is a good example of a second-class lever. On the other hand, when we bite into food, when we're initially biting, we use our canines and incisors, our mouth is operating as a third-class lever. This is where the force is in between the load. This is where the force this is where the force is in between the load and the fulcrum. So if this is our mandible and this is our TMJ, we're going to exert a force in the middle of that and the food here. And that is called a third-class lever. And that is my presentation on the physics of the human mouth and chewing in the human mouth. These are my works cited, and then these are the my works cited for my pictures in my example. Thank you very much for your time.